Yeah. So now we are recording. So that means that everything is going to go on YouTube. So yeah. But anyways, we're going to go over the equation sheet. I have the chat open, so if you have any questions, ask. Feel free to ask, and I will answer them. But here we go. So the formula sheet, it's very long. We've got a lot of information here. So it's worth knowing how to look through it. So if you guys have this, print it out. I highly recommend annotating it yourself, like noting what variables mean what, when certain equations apply, and stuff like that. That's a very helpful tool. It will save you some time on the exam. And it's not against the rules because Dr. Herrera did say you're allowed to make your own equation sheet. So that's allowed. I do think you guys have to turn it in. I don't quite remember, but yeah, you're allowed to mark it up, which I do recommend you do. So first things first, we got the first page here. There's nothing super exciting here, just some vector identities in the first box, then some geometry stuff. Remember this geometry stuff, that's useful when we use Gauss's law, like the volume of, specifically the surface area. So remember, if you're integrating over a sphere, integrating over the surface of a sphere, I mean, then you're going to need to know these formulas. And so they're given to you right here. So just remember, you don't have to like memorize the area of a cylinder, stuff like, actually you do have to, you can piece together the area of a cylinder, but things like an area of a sphere or a volume of a sphere, you don't need to know off the top of your head. That's given to you. And also, this is surprisingly useful, especially when they give you questions involving things orbiting in magnetic fields. If you ever are asked about that, this is a surprisingly useful identity. So just remember this: 1 revolution is equal to 2 pi radians. Very useful, surprisingly useful. I wouldn't say very useful. And then we have some physical constants here. So if mu naught, you may not have that one committed to memory yet. So remember, this is the magnetic permeability of free space. So if you ever see a mu naught, this is what it's just 4 pi times 10 to the negative 7. So this is just a number you know. It's not a variable. And remember, the charge of the electron is negative. So if you're this is on the exam that we're going to go over, but like if you're calculating a force on an electron, so remember that minus sign will matter. So if you're using the right hand rule to tell you the force, and then the force tells you it's going in a certain direction, then if it has a minus charge, it's going to be the negative of that direction, so pointing in the opposite. Please keep that in mind. That is important. But now we can move on to some actual equations. So fluids are on this exam, and the structure of the exam usually goes, it's the old stuff first and then the new stuff later. So like the optics usually is at the end of the exam and the fluids are at the beginning. So if you feel like you're weaker in a certain area, like fluids, like it's been a while, you can work the test backwards and like leave that to the end if you, that might help you out. Just a test taking strategy that I recommend. But yeah, so just remember P. So P and rho look very similar, but they mean different things. So this is a rho. That's a Greek letter right here, and dm, dv, that just means density. So don't let these differentials scare you. Like that just means like the derivative of mass with respect to volume, but really it's a density. And you're never going to be given a fluid that depends on like a certain volume. That would be a far too difficult question for this course. So this rho is going to be a number, like it's the density of water, density of mercury, something like that. And then you're just going to have to apply these equations. So this first one here only applies for static liquids. So if your fluid is moving, this is technically not true. You have to be a bit careful there. So just be careful with this, but remember, all it's saying is the pressure at the bottom is equal to the pressure at the top times the weight, really the pressure due to the water above you or liquid above you. That's all this equation is saying. Then we have the buoyant force. So this is real useful. So it's saying, if you have a density times a volume, well, density times volume is a mass, and you multiply that by gravity, that's going to give you a force. So it turns out that so this is the weight, right? So it's a mass times gravity. That's exactly equal to a weight. So a mass times gravity of the displaced fluid is going to be equal to the buoyant force. So you just take that as fact. dv dt is equal to av. So this is just like flow rate. So this just means like how fast is if you take an area and multiply it by a velocity, that's going to tell you how much volume is moving through your through your pipe. And this is useful. It's called the continuity equation. And this just says if you have the same amount of mass going in, you have to have the same amount of mass going out. Otherwise, you have mass accumulating somewhere, which is not something we deal with in this class. And then we have this equation that looks very intimidating, but it's not as bad as it looks. So this is Bernoulli's equation. If anyone ever says Bernoulli's, this is what they mean, at least in the context of fluids. And all it says, so just look at one side for now. We got pressure on one side plus 1/2 rho v squared. That's a kinetic energy, and then this is gravitational potential right here. And so we know energy is conserved. So we're saying like the force on one side plus the energies is equal to the force on the other plus the energies on the other side. So it's really just a statement about conservation of energy with a bit of technical stuff thrown in with the piece, but don't worry about that too much. So that's fluids. Not a huge portion of the test, but it is a good idea to refresh yourself if you need to, because I guarantee it will be on the test. So now we have electrostatics. So we spent a lot of time on electrostatics trying to derive these formulas, like the E field for a point on a sphere or a line or a plane, and use that using Gauss's law. So Gauss's law, very useful. Having a conceptual understanding of it is very important. I would say you're very likely to find a question about it on the test, but you're probably not going to have to rederive an electric field from scratch. It's not impossible. It's definitely possible that it'll ask you that. But on this exam, I went through the whole thing. There wasn't a question where you had to rederive a certain kind of electric field. So just keep that in mind. So these are different charge geometries. Remember, depending on how the charge is distributed across some sort of surface, then you're going to get a different E field depending on that. So the important ones are listed right here. So if you have a point or a sphere, you can use this E field right here. So if you look carefully, this is just like Coulomb's law with one of the Q's removed. So you remember that gives you like an idea of what this definition is. Because you divide the force, which is Coulomb's law, divided by one of the Q's, then you're just getting one Q on top. That's the idea. So the line charge, this lambda, refers to charge density, linear charge density. So it's just saying, I have a line that is this long, and it's got this amount of charge on it. Then I divide those two numbers. I say, what is the total amount of charge divided by the length? And then I get lambda. That's what it's saying. So lambda, in general, can be a function of length along the wire, but that's all it is. So lambda is just a line charge density. And then similarly for sigma, sigma is a area charge density. So now I'd say I have an area, and I take the total amount of charge I have and divide that charge by the area, and then I'll get sigma, if it's uniform. You have to be careful when it's not uniform, but a lot of the times it is. So we got other definitions here, like this is an electric dipole moment. That's P, right? That's what P stands for there. This is the torque on an electric dipole and the potential energy of an electric dipole. So those are given here. Just remember these are vectors. You should be fine. So now we have the definition of electric flux. So this is a surface integral. Remember, in this class, you don't ever have to do actual surface integrals. It's beyond the scope of this course. You don't have to have Calc 3 under your belt to do it. But what you do need to know is, so long as you have your area vector and your E field vector parallel to each other, so they're pointing in the same direction or against each other, in that case, then you can just take its E times the surface area of whatever surface you're integrating over. So that's the idea behind electric flux, and you can use that very nicely when you're trying to calculate E fields using Gauss's law. So this is Gauss's law right here. E dot dA is equal to Q enclosed divided by epsilon naught. If you look carefully, this is the same thing as this, right? So it's an integral of E dot dA. So the electric flux is equal to E dot dA integrated over a surface, and then you look at how much charge is enclosed in that, and then you can figure out the electric fluxes. So that's Gauss's law. And then you've got some definitions on electric potentials. So I think this is the most useful right here. So the potential difference is the negative line integral of E dot dL. So all it's saying is if you were to go from one point to another point, you add up how much the E field helps or hinders your movement along that path, then that's going to give you your electric potential. And technically this is like potential energy per unit charge. So if you are ever asked about potential energy, it's related to V, but it's not the same thing as electric potential. So do be careful of that on the test, because they could do a bit of a get-you question for that. So yeah, you have to be careful. So this integral becomes what I just highlighted here when the E field is constant. If it's not constant, you have to be careful. But yeah, when it is, your life is a bit easier. Okay, so that's all we have for electrostatics. Now we have capacitors. So we have a lot of stuff here, but really, we can talk about it. So this is the definition of capacitance. This will hold for any sort of capacitor you have. So remember what a capacitor is. It's just like, in the most simple case, it's just two plates, and you put some charge in those plates, and you say, well, they've got positive charge here and negative charge here. And then that's going to create an electric field between the two, and that electric field creates a potential difference. And so you take the total amount of charge on each plate divided by V, that's going to give you capacitance. But, the math works out nicely here, and you don't actually need to have a charge on something for it to have a capacitance. So in general, capacitance is a completely geometric quantity. It doesn't care about how much charge you put on it. It cares about like how big the plates are, how far apart they are from each other, that sort of thing. So this is the simplest case where you have two parallel plates. That's what this equation describes. This equation right here is for a cylindrical capacitor. If you have if you take a line and then you wrap like a metal sheet around it, that's going to create a cylindrical capacitor. And this is a spherical capacitor right here. So yeah, it's worth writing that down because they're not labeled for you. But you can rederive these if you need to by just integrating and figuring out what V is for each of those charge distributions, but you guys don't have time for that. So I highly recommend writing that down. And this is actually just a special case of the last one. So this is, you can have a capacitance with respect to your outer shell being at infinity. And that's what the highlighted equation here is referring to. If you have your outer shell and you take it go way far away, then its contribution to the V is going to go away, and you're going to end up with that equation right there. So this is telling you if you insert a dielectric, this is how it changes things. So dielectrics, if you remember, is just some insulator, and you slide it in between those two parallel plates or whatever the geometry might be, and it's going to have a number associated with it. All you have to do is multiply that number by your capacitance without the dielectric in it, and then you're going to get your new capacitance. So that's all those two equations say. And then we have combination rules and the rules for energy stored in capacitors. So the energy stored in capacitors, these are all equivalent. So you can get from this equation to this equation by substituting this in. So they all say the same thing. It just when to use which one, it depends on what you're given in the problem. So it takes a bit of practice, but you can always get the others. So don't worry too much about this. And then this is just energy density. So this is energy. This is this divided by volume. So it's the volume between the plates is what it means. Okay. So no one has any questions so far. So I'm going to keep going. I will try and finish up in the next 10 minutes, but there's a lot of stuff to talk about. So we got electric current and resistor circuits. This stuff isn't too bad, so I'm going to kind of skim through it. So this is the definition of current. We got Ohm's law right here. Hopefully that's pretty familiar. And then we have microscopic Ohm's law. So J just refers to current density. So you take your current, divide it by an area, you're going to get J. So don't be intimidated by that. And then this is actually microscopic Ohm's law. So it says the E field is equal to your current density times your resistivity. So that's what rho stands for. It's just like a material property. You can treat it like that. So this is how resistance is going to change with temperature. Or sorry, this is how resistivity changes with temperature, and this is how resistance changes with temperature. So we got our combination rules, and then we have power. So this is true for any circuit element you have at any time. Power is equal to IV, and then you can substitute Ohm's law in to get these other I squared R and V squared over R. You can always substitute Ohm's law to get those. So remember for AC LRC circuits, this still applies for any component. If you want to figure out the power dissipated across the resistor or the inductor or something like that, that's actually a bad example because you can't dissipate power over an inductor. But you still use this formula. Yeah, so over an ideal inductor, I should say. Okay, so now on to RC-DC circuits. So this is just a circuit where you have a resistor and a capacitor. That's where RC comes from. That's what it stands for. And DC, remember, there's nothing fancy happening with our batteries. This is a simple battery hooked up to a resistor and a capacitor. That's when these equations apply. And so this is for a charging capacitor. it describes the amount of charge you have sitting on your capacitor. And this is a discharging capacitor. And then you have the definition of your time constant, RC, and then if you take the derivative of this, you're going to get this. Yeah. So that's all for that. And now we move on to magnetostatics. So this is when the course might have become a bit less intuitive. Magnets behave a bit weird, but we've got all the equations, we've got all the info we need here. So we've got the magnetic force law here. So this is actually the Lorentz force. If you have an E field, then you have to include that here, and that'll give you the total force in your particle. But oftentimes you can ignore the E field to be zero in problems that involve magnetic fields. And so it just ends up being Q times V cross B. So don't get intimidated by this cross product. Remember to use the right-hand rule, and remember that the order matters for the cross product. You're going to get a minus sign in the wrong place if you do B cross V. So we have dF is equal to I dL cross B. So I think this tends to be very intimidating to a lot of people, the fact that we have these differentials involved in these formulas now. All it's saying is that if I have a wire, and that wire is bent up in some weird curvy shape, then I can't say that the force on that wire is going to be like this number in a certain direction, because like different parts of the wire are going to experience different forces, because the B field may be the angle between the B field and the current is going to be different depending on how the wire is bent. So we say, well, we're going to ignore that, and we're going to chop the wire up into tiny little sections, and then just care about those tiny little sections. That's what the differential really means. So with that in mind, all this is saying, if I want to figure out what the force is on a little bit of a wire, so, with length dl, then I just take the current in that wire and I cross that into B. So that's what it's saying. And then we have definition of magnetic flux here. This is the radius of curvature for a particle that's orbiting in a B field. So remember, if you have a particle at a certain velocity and the B field is perpendicular to that velocity, then the velocity is going to just kind of keep turning around. It's going to undergo circular motion, and the radius of that circular motion is given by this formula right here, which you can get by using some 221 stuff. So this is the definition of a magnetic moment. Remember, IA is referring to the area of a loop, so you have to have a loop in order for a magnetic moment to exist. And then we got torque and potential energy right here as well. So now we have we've got the magnetic force law for a particle. So this is just saying, if I have a particle moving through space in a B field, this is what I'm going to use to describe it. So the reason we have an R cubed on the bottom here is you have to be careful. Notice that this is an R hat there, and this is not an R hat. So R hat is just R divided by the magnitude of R. So that's why we have R cubed on the bottom here. Otherwise, these formulas are exactly equivalent. So, just go step by step if you ever have to use that. You guys can do it, I promise. So now we have the really intimidating one, the Biot-Savart law. And it's a differential on this side and another differential here. So whenever you use it, if you want to figure out what the total force is, you're going to have to integrate, which is scary, but often the integral ends up being pretty easy. The way to approach problems where you actually have to use this formula is you write down the formula first, you pull out all the constants, because usually R is a constant, and you figure out what this cross product is, and then you integrate. Integrating should be your last step when you do a problem involving that formula. Now we have Ampere's law. Ampere's law is it's very useful for rederiving this. Otherwise, in this course, it's not super helpful because most of the other formulas are given to you, but it's really nice if you ever need to figure out what the B field is for a complicated charge sheet, complicated current density. But I wouldn't worry too much about it. The idea is you draw a circle around some sort of current, and then you count up how much current is inside of that circle, and then you integrate over the perimeter of your loop. So it doesn't technically have to be a circle. It could be a square. It could be whatever shape you want. But the perimeter of that shape is going to give you is going to be a function of the B field. And that's the idea. Okay, so we have a lot of equations at the bottom, but all of these are just charged. They are B fields for different current densities. So like if I have a long wire, that's just one long current thing we've got, and then the B field is given by this. And then the solenoid, remember, that's just like a spring, so it looks just like a spring. Then the B field inside of that spring is given by mu naught n times I. And so a toroid is a donut, and a loop is just what you think it is. And then so F divided by L, this is the force per unit length on a wire. That's what this equation refers to. So you need to have two wires. That's why there's I and I prime there. Okay, we got 4 minutes. I'm going to try to finish this up within that time. So I'm going to kind of breeze through induction and inductance because there's a lot of heavy calculus here. But the idea is, if you want the EMF induced, like this is, I'd say this is the most important equation right here. The EMF induced in a loop is given by the change in the negative derivative of the magnetic flux through that loop. So if you have a loop and the size of that loop is changing in a B field, then it's going to have an EMF induced in that loop. And then, or if you have your B field decreasing in time, it's also going to induce an EMF. So the minus sign, just remember that's Lenz's law, and it just says it's going to be in the opposite direction of the change. So the loops don't want to have their magnetic flux changing. They would rather they create currents to preserve the magnetic field that's going through them. So this says the exact same thing right here without the n. So this, you say n equals 1, then you get this formula right here. Remember that EMF is really it's a line integral of E field. So we got equations for inductance here. So L is inductance. It's just a number that quantifies how well something can like keep a current going through it. How much does it want to preserve that current? So if I have an LC circuit, if I have an LC circuit, so these equations are semi-important. If I have an LC circuit right here, so this is the this equation I highlighted is going to describe the charge sitting on a capacitor, this is what omega is. So if I have a charged capacitor and I hook it up to an inductor, that's when this equation will apply. If I have a resistor connected to a charged capacitor and an inductor, this is what the equation is going to look like to describe the charge sitting on that capacitor. So the rest of it isn't too bad. Remember the same deal. So you can store energy in an inductor just like you can store energy in a capacitor. Same idea, it's just with magnetic fields instead of electric fields. So now we're to AC/LRC stuff. So this is this looks intimidating. There's a lot of information here, but this stuff probably won't come up. It might. I can't say it will. It's not worth ignoring, but it doesn't come up often. I haven't seen a test where it has, but you know, it's worth learning. So V equals IR still applies here, but we have to be a bit more careful because now we have an AC circuit. So the resistance of these two things are going to depend on how high our frequency is. So AC means you got current. Your current is switching directions over time. So your current's pointing one direction and then pointing another, and then keeps switching between those two. That's what AC really means. And so if we look at our formulas for XL and XC, there's both an omega in there. So we have to keep in mind that changing omega is going to change XL and XC. So thing I want you guys to really take, like the most important thing is that for an AC/LRC circuit, resonance happens when omega is equal to 1 over the square root of LC. That's really important. It's worth writing down if you haven't already. So resonance just means that when XL is equal to XC. So XL is equal to XC when you have omega equal to this. So you can do the math to check if that's true, but I promise it is. And then we have a bunch of rules here. So Z is equal to this. Follow the equations and you'll be A-okay. It's just a lot of stuff to keep in mind. Yeah, so now things become important. Now that we have changing current, you have to average over one time cycle in order to get this, but follow the equations, you'll be okay, I promise. So these are the only equations we have for transformers. So the math is not very hard if you have a transformer problem. Just kind of, so just this is all you're gonna need, I promise. So complex impedance, everyone who came to sessions asked me about complex impedance, which is fine, it's complicated. The idea is, so if you have a complex number, that complex number can be represented as like a vector in the complex plane. So if you have it, that j represents the square root of -1. So so the j component is like your y, and then the r in this expression right here. So the j represents like j hat. You can think of it like that, and then this r is like the x component of that vector. So it's sitting in the complex plane with some sort of angle with the x-axis, and that's very similar to when we were drawing these phasor diagrams. So the idea really is, it's just introducing complex numbers is just a nice way to deal with these phasor diagrams, because like the geometry works out exactly the same. So and these rules for combinations, all it's saying is if I have a certain kind of circuit and I plug it in like in series with another circuit that also is like depends on the AC frequency, then this is how I combine those. That's the idea. And then we have different rules for how to work with complex numbers, but yeah, don't worry too much about that because it didn't come up. Maxwell's equations. So you've learned all of these before, but yeah, so you got Gauss's law, you got no magnetic monopoles, you've got the law of induction here, and then you have Ampere's law. So just a note here that it's got the correction term, because if you have remember the example with the capacitor, you have a capacitor, you need to account for the changing electric field because there's no actual current that's going through that thing there. Okay, so now we're to the new stuff. I'm gonna try to go fast. Ask questions if you have them. So if you have an electromagnetic wave, the E fields and B fields are going to look like that. They're always going to be in phase, unless they're in some sort of weird medium. So E fields and B fields are in phase for electromagnetic waves in a vacuum. So in a vacuum, your speed of light is known. It's c. It's 3 × 10⁸. So it should be on your equation sheet somewhere. I'm not 100% sure, but if it's not, do write that down because it's something good to know. Yeah, it's right here, so you can calculate it. Yeah, so the speed of light, if you know that, it's really easy to figure out frequency or wavelength because it's just a function. It's this nice simple equation, and this will hold for any sort of wave. It doesn't have to be an electromagnetic wave. It could be any wave you want. The speed of that wave is equal to the frequency times its wavelength. And then we have some definitions for different quantities. And a lot of different things, like if you want to figure out the energy density in a wave, use these equations right here. And now we have the Poynting vector. So it can be a bit weird to think about the Poynting vector, but it's the Poynting vector, it points in the direction of propagation. So if I have a wave, that wave is going to be moving in some way, and the Poynting vector is like a way to keep track of which way is that going, as well as the Poynting vector is equal to intensity is equal to power per area, I believe. But you don't need to know that. So the average, it's power per area, that's right. So I is equal to S average. Like there's a bunch of equations here. All you need to know, the I is intensity now, not current. So we're running into some problems. We have to reuse variables, but I is intensity here. And then we have a bunch of equations. Remember, these are all equivalent. You can get these by substituting this into here. And it's equal to S average. And if you ever need to calculate an intensity, like if you're given an E field, you need to figure out the B field, you use this rule right here. This equation, it tells you about radiation pressure. That's what it is. So this dp dt, this is momentum. That's what the P is referring to. So this is actually a force. So if you want to erase this or mark it up somehow, this means force per area is equal to S divided by C. That's very important. If you have any sort of question about radiation pressure, this is what you want to use. And then we have Snell's law right here, very useful. So the critical angle is given by N2 divided by N1. And yeah, other rules right here. So now on to the last section, interference and diffraction. There's a lot of info here, the stuff to keep in mind. So when you have m is equal to an integer number, so m can be 0, 1, 2, 3, 4, or 5, and so on. It can be any zero or positive integer. That's what m is. It's just an index. It's keeping track of which peak you care about. So that is important. And so if you want constructive interference, you have m equal to a full integer. If you want destructive interference, you have m equal to a half integer. So that's what this 1/2 is means. These equations apply for destructive interference. This equation applies for constructive interference. And then we have our intensity law right here, what these things are. This is useful. How does wavelength change when it enters a medium? So wavelengths get shorter when they reach a denser medium. That's the idea. With that, we got the definition of beta, sine of so this is how intensity, remember, so these are intensities, what I is referring to here. And then we have the resolution. So this 1.22 is arbitrary, but it's what we use in this class. And yeah, the rest of this doesn't really come up a lot. If you guys have any questions, please ask. So that's the equation sheet. It was a lot of me talking, like a good solid half hour of just me speaking to you. Does anyone have any questions before we move on? All right. Okay. E field of a plane. Okay, so back up to electrostatics. Yeah, so it depends on the sign of remember, you may remember if you use Gauss's law, then the E field lines, if you have a positive charge sitting on the outside or on a surface, so imagine you have just like an infinite plane, and on that plane it's got a certain amount of charge per unit area on it. Then either way, if I'm on one side or the other side, then either way, the E field is going to push me away from it. So that's what the plus and minus is referring to. The plus and minus just says like, it depends on which side of the sheet I'm on. If I'm on this side, if my sheet is sitting here, then I'm going to want to go this way if it's a positive charge. If the sheet is sitting here, I'm going to want to go that way. So there's a discontinuity in the direction. That's what the plus and minus means. Yeah, that's a good question. Okay, so if you guys have any other questions. Okay, so Presley's got a question. Let's say you're looking for destructive interference and there's only one phase shift. Use the equation for constructive interference then? Well, so I think you have to be careful because like a phase shift is arbitrary, right? It depends on how big the phase shift is. If it's a phase shift of one full wavelength, then it would be constructive interference. If it's a phase shift of a half wavelength, that would be destructive interference. Yeah, so you have to be careful about what the phase shift is. All right, these are great questions, guys. Keep them coming. But we should probably get into some problem solving now. So here we go. We've got, so first some explanation. I didn't like write this exam myself because I don't have that sort of time or expertise. But here's the deal. So it's a little bit confusing to read this exam because it's got a bunch of parentheses. So ignore whatever is in the parentheses. What we're going to do to make sure that we're all on the same page here is we're going to be using the first number. So the first number is referring to the first version of the test. So like anything you see in parentheses next to a certain quantity is going to be the alternate test version, and we're only going to deal with the first one. So like for this first problem, we have a ship passes from a freshwater lake to the saltwater ocean. So we're not concerned with what's in these parentheses. And so to make sure that everyone gets a consistent answer, just ignore what's in these parentheses or square brackets or anything like that. All we want to do is take the first number. So hopefully that makes sense. Ask questions if it doesn't. But yeah, we're ready to get started. So I'll zoom in a bit and you can read the question. So what we've got is a ship going from the freshwater lake to the saltwater ocean, and we want to know how does the height of the ship in the water change when it goes from the freshwater to the saltwater. All right, Christian's already got an answer. I'll give you guys a bit more bit longer of time. I do want to say, if you guys haven't put your net IDs in the chat yet, please do so, so I can get you guys marked down. So far, we have a unanimous response for A. Awesome. All right, I'll give you guys just like 30 seconds more to think about it in case anyone is still confused, and to give me a second so I can put in some names. Okay, so everyone thinks it's A. Is anyone brave enough to tell me why they think it's A? No one is brave enough, huh? What if I told you A is correct? What about that?
The salt water is going to be more dense than the fresh water.
Yes. So can you tell me what does the density of the water mean for the force on the boat? Yeah. So Ethan is exactly right. More buoyancy force because the density of the displaced liquid has gone up. So it's going to take less of that displaced liquid to weigh the same as the boat. That's the idea. So yeah, very good, you guys. That was really fast. Awesome job. So next question is a bit more quantitative. We've got water entering a pipe, or water pipe entering a house at a certain depth underground, and then it's going up to a certain height in this house. And we need to know what the pressure is at the top of the house. So what is the pressure of the water up there? No, that is not true, Andrew. So that's a very good point. It does seem like D would be true, but it's not for number one, because the buoyant force has to be equal, because if it was bigger, well, so that's a good point. It does experience an increase, but really it's the same, because it's the condition for equilibrium, right? So the forces need to be balanced. If the force increases, then you're going to be accelerating upwards. So it's not so much that the force increases. Yeah. V displacement is smaller to have the same amount of force. So it's going to be higher up in the water, is the idea. Yeah. Thank you, Ethan. So I would like to check, is anyone completely stuck on how to start this problem? All right. So no one says they're completely stuck. So I'm gonna keep my mouth shut then. please do let me know if you guys do have answers like you did last time. That is how I like to have these sessions run, is because it helps me know how much time you guys need, where the group's at.
In Bernoulli's equation, is h going to be your height or your depth?
That's an excellent question. I think so. You want it to be. I'd say it's arbitrary. Really, what matters is the difference between the two. So just set your 0 wherever makes sense to you, and then, like so long as h2 is the same distance away from h1, it doesn't matter. Is my answer to that. The answer is yes, Andrew. So Andrew, yeah, if y1 is below ground, yeah, it would be negative, but it doesn't necessarily have to be negative, right? Because you could set your 0 for your axis to be there. Yeah, exactly, Ethan. So you could set your 0 to be that, and then it removes a term. So yeah, you could do that. Whatever makes most sense to you. And you can actually see that in the algebra, because if you rearrange Bernoulli's equation for what you're solving for, you're going to find that it's h1 minus h2. So like, what really matters is the relative difference between them. Yeah, it is a lot of numbers, and it can be, especially since they have all these brackets and parentheses everywhere. It can be hard to figure out which one it is. All right, so I've got 1 vote for B so far. I'll probably give you guys a minute or so more, maybe 2. All right, so Christian is also getting about 1.1 times 10 to the 5th. Yeah, that is a little bit off. Now, it could come down to rounding. Not sure. All right, yes, thank you. I got to put Kai's name in. Yeah, we'll go through this as soon as I put Kai's name in. That was odd. Okay. Cool. That's all right, Kaya. All right, so are we okay if I run through this? Or do people want more time? It seems like the majority of you guys do have answers. No one wants to give me confirmation. I'm gonna run through it. I spent a lot of time on the equation sheet, so I'll try to keep the pace going. Awesome. So we're good to go. First things first, let's try sketching out what's happening. So we'll talk about the problem. We've got a water pipe, it's entering a house and going up, and we want to figure out what the pressure is at the top. So we've got a pipe that's doing this sort of thing. What I'm gonna do, when I did this problem, I set my 0 to be right here. So this is like the ground. It doesn't matter. You can set your 0 to be wherever you would like. And, as we talked about, all that matters is the relative difference between height 2 and height 1. So those are the two relative distances, and I'm gonna label the velocities of the water in the pipe. So I'm gonna call it V1, and the velocity up here is in V2. And all of the quantities they've labeled here are known. They are given to us in the problem. The equation we're going to apply here is Bernoulli's. So how do we know to apply Bernoulli's? Well, we have moving liquid, and that's really the only equation we have that describes moving liquid. So that's one way we can know to use it. Another way is that we've got one point and another point. And so Bernoulli's is really good at connecting fluid flowing from one point to another point. Bernoulli's is very good at that. So let's write down what it says. I rearranged it a bit from the equation sheet, but it means the same thing. So here's what it says, and then plus P1. So the third term here is actually pressure. Just be careful there. So rho GH2 plus 1/2 rho V2. So it's the same thing, but with 2's in the subscripts. So what are we after here in this expression? This is the thing we want to solve for. So to do that, we're going to move some terms over, and we're going to rearrange. So I'm going to skip the algebra, and we're going to get the following. So it's just a matter of subtraction. And so someone pointed out, I don't quite remember who, they pointed out if you set H1 equal to 0, so if you shift this number down by a number of H1, then you cancel out one of these terms, which is very convenient, and that's an excellent point. You can do that, I think, every time. So it's not a bad idea to do that, but I think this is most clear. You don't have to, is my point. V1 squared minus V2 squared. So notice you got to keep the squares on both of these quantities here. You can't bring the square out. Just an important math thing there. And then plus P1, and this whole thing is going to be equal to P2. So we've got that, and now the only thing we have to be careful of is this H1 should be negative for us. So in the problem we're told H1 is 2 meters below ground, so this is going to be a -2 when you plug that into your calculator. So you do have to be careful with that. But other than that, we know everything that we need to plug this in. And when you do so, you should find that P2 is equal to 1.08 times 10 to the 5th, which is about 1.1 times 10 to the 5th pascals. So the answer is actually Christian, I'm not sure where you might have gone wrong, because I'm pretty sure you used the right process if you're getting close to the right answer. It might have come down to just plugging in numbers. I don't think a rounding error though, because that is a pretty large difference. I would suspect you might have used the wrong second velocity. Not sure though. Okay, so yeah, that's that question. Now we have number 3. A point charge plus Q is placed 10 centimeters. Yeah, it happens. Yeah, don't worry too much about the. Yeah, Christian, if you're not using 9.81, that might be the problem. All right, I'm getting distracted. Yeah, so we've got a point charge. So now that's the fluids portion. There aren't any more fluids questions on this exam. What we've got is a charge, and it's placed a certain an equal distance from a point charge and a line charge. And we want to know what is the size of the point charge that's keeping it there. So sketch this out if it doesn't make sense right away. But yeah, it's not super complicated, I promise. Okay, yeah, I mean, I thought you were using 10 or something. Yeah, I guess you can drop the 1/100th. That's not a problem with me. Yeah, I guess using 9.81, it varies depending on where you are on the Earth. Because like if you're on the equator, you're moving around faster. I did this problem in intermediate mechanics. If you're standing on the equator of the Earth, like you weigh less than if you're standing at a latitude of 45 degrees, or however latitude works. I don't remember. All right, Andrew's already got an answer. I'm flying through these, man. You do want to be careful with the orders of magnitude in this one, because as you can see, 3 of these answers are within orders of magnitude of each other. So I do recommend double checking those. Oh, sorry. Okay, so Andrew's got an answer. Is everyone else working, or are people stuck? We need to push in the right direction. Okay. Yeah, I'll give you guys some more time, and I am okay with letting this session run a little bit longer since it is the last SI thing I'll be doing for the semester. So like if we end 10 minutes late or early, or it won't end early, I promise. I am okay with that, but I understand people have other things to do. All right, so Kaya thinks it's E. All right, Christian thinks it's E as well. All right. I'm going to give you guys like 30 seconds more. So if you're plugging in numbers, speak now or forever hold your peace. Or not now, but within the next 30 seconds. All right, so I'm going to let you guys know that E is not correct. I don't know, unless I misread the solution manual. I did not get E, but let's go through it. It's not C either. Let's go through it. We'll run through it and then we'll talk about it. So first things first, we're gonna sketch it out. So what we've got is a point charge Q sitting up here, and then we have a line charge with linear charge density lambda sitting below it. I'm not going to tell you yet, Christian. I can't give away the suspense. So let's label our diagram. I'm going to call this distance D and this distance D. So just remember, this is half the distance that we're given in the problem, so it's 0.05 meters. Be careful with that. And so Q is what we're looking for, this Q that I just labeled or circled here. So now all we have to do is figure out what the conditions we're looking for, right? So we're told that the net E field at the point I just point in between these two, the dot that I have, is 0. So let's describe the E field for both of them. So I'm going to call the E field of a point charge. I'm going to write that down. So I'm going to call it E sub. I'll call it E1. And I'll say that's equal to K times big Q divided by R squared. So this is on your equation sheet. You don't need to read or write that. And so is this one. So the E2 is the E field due to the line, and that's equal to 2K times lambda divided by R. So remember, K is the electric constant. It's 1 over 4 pi epsilon naught. Okay, and we know that the net E field is 0. And we also know if if we assume lambda and Q are positive, that means the E field is going to be pointing up due to the line charge and down due to the point charge. So really all we're looking for is when E1 is equal to E2. There's no minus signs or anything fancy with that. So E1 is equal to E2. So that's the same thing as saying K times Q divided by R squared, but I'm not going to use R, right? Because we labeled our distances as D. So we're going to say this. And now we have to solve this for Q. Yeah, I think it just came down to the D being 0.05 instead of like 5 or 0.5. So we cancel things out, and then we do a bit of algebra, and we find out we end up with Q is equal to 2 times D times lambda. So when we plug in, D is going to be 0.05, so it's going to cancel out the 2. And when we plug that into our calculator, we find out it's 1 microcoulombs. So that's actually answer B. So yeah. that's the answer. So that's how you get it. I think it really just came down to plugging in numbers, you guys. So don't feel too bad if you didn't quite get that one. Like plugging in numbers is the least interesting part of physics, in my opinion. No one cares about whether or not you can use your calculator correctly. At least I don't. All right. So what we've got here, next question, is it's a conceptual question. We've got a solid metallic sphere. It has a net positive charge, and we want to know which of these graphs describe the radial component of the electric field. Yeah, I'll give you guys about a minute on this one. I don't think it'll take too long. All right. Man, I haven't done this much talking in a while. My voice already hurts, you guys. All right, so far we got three votes for C. And there's far more than three of you, so if you guys have an answer, even if it's a guess, you go ahead and put it in the chat. No one will judge you. Or at least I won't judge you. I guess I can't speak for everyone, but this class is hard. It's okay to be wrong. That's my point. All right. Let's go through this. This is a pretty quick one. Does anyone want to tell us? Okay, so Ethan is sure about the after you're outside. Yeah. So it's between C or A, and so yeah, there's one important fact we need to answer this, and that is the fact that this is a solid metallic sphere. So in this class, a metal means that it's a quote unquote perfect conductor. So in perfect conductors, you have no net E field. So that's just kind of a fact that comes from, like, you can prove it from Maxwell's equations, but the E field inside of a conductor is zero. You have constant potential, but not constant E field. You have zero E field, which is a constant actually. Anyways, the correct answer is C. So we'll talk through why that is. So like I said, inside of the conductor, there is no E field. So why is that? You can think of it as, so we're told it's a sphere. So if I drew a Gaussian surface inside of this metallic sphere, then yeah. So if you read it as, yeah, so insulating sphere. Okay, yeah, Ethan. So that's fine. But yeah, back to what I was saying. If you have a if you draw a Gaussian sphere inside of the sphere, so it's sitting inside, then the enclosed charge inside of there is zero. And that's really the reason why the E field inside of a conductor is zero everywhere, because all of the charge sits on the outside. So that's the idea. And then once you're outside, it's going to behave just like a point charge. So it falls off like 1 over r squared, which is why we have this shape right there. So C is the correct answer. And yeah, if it was insulating, then A would be correct, because then you'd have, it would depend on how the charge is distributed, but usually in insulators, charge is distributed uniformly, and then you'd be constantly increasing charge. So yeah, C is the correct answer there. On to number 5. This is about an insulating sphere and then a metallic shell. So on the inside here is an insulator. Sorry, no, yes, that's correct. So the inside is an insulator, the outside is metal. So that is important. All right, Caden thinks it's B. Yeah, I think this one is a bit is a bit harder to think about for a conceptual question. So if anyone is confused, all right, so we got another vote for B. Do ask questions if you guys have them. I can't help you if I don't know what's confusing you. All right. So, Christian, the way you phrased that really made me think that you were confident. All right. So no dissenting opinions yet. Ah, there's one. Okay, so we've got a few answers. Do we want to talk through this, or do we want more time to really think deeply about it? I think the biggest hint I can give to this is that so we established in the last question that the E field inside of a conductor is 0. So remember that so this is asking about electric potential. So the electric potential inside of a conductor is a constant because the integral of 0 is going to give you that plus C. So it's just going to be one constant value. So inside of this metallic shell, that means that it's going to be the same value. So VB is equal to VC. That narrows it down to A, B, or D. Yeah, so that could be a nice a rule of thumb to check. You know, if you're given a problem like this and you're not really sure, just start with the simple things. We know that the inside of a conductor, the E field is 0, and that the potential is a constant. Yeah, so the reason that VB is equal to VC is that we know the E field inside of a conductor, so a metal, is equal to 0, right? So we said that in the last question. So if inside of there it's the E field is equal to 0, you can't have any sort of net force, right? If I don't have an E field, if I'm a charge sitting inside of there, I'm not going to feel any net force due to the electric field. And so, if that's the case, that means I can't have any difference in potential, because remember, electric potential is telling you which way does a charge want to really roll. Is it it wants to roll downhill to a lower potential? But if I have a flat line that describes my potential, then there's no way I want to roll. So if my potential looks like that, that means I can't have a net force. So that's one way to think about it. Another way is, we defined the potential as the integral of the E field. So the integral of 0 dx is equal to plus C, right? So if that's the case, then that C is equal to the value of your potential. It's just some constant. That's completely arbitrary. You're allowed to choose that. But yeah. So, okay, we spent a good chunk of time on this question. The correct answer is B. So let's talk through it. So a lot of you chose it. Like I said, that we know that the voltage inside of the conductor, so VB is equal to VC because it is a conductor. So if we scroll back up, if we integrate just on the inside of here, that's 0. So we see this is the E field right here. If we integrate E field, we get voltage. And technically, if we integrate E field with respect to distance, we get voltage. So if you do that, you get a constant, and that constant is going to give you the same voltage. So the constant may be 0, but that's the idea. And so how do we know that VA is greater than VB? Well, we know that we have we're going to have a charge on the inner surface here due to Gauss's law. You can use Gauss's law to figure that out. And so if you have that, you have you're going to have a charge of -1 q on the inside, and due to that, you're going to have an E field pointing from here to here. And so if you were to take a path that goes from the inner surface of your shell to the outer surface of your conductor here, you'd have to go against the B field, and that's going to add up to your potential. So VA is the highest potential you can have, and VB is kind of the lowest on the inner surface here. So B is the correct answer. Hopefully that explanation makes a little bit of sense. The way I think about it is like, if I were to take an electron and or a positive charge, not an electron, if I were to take that and just kind of pull it around, then which way does it want to go? If it doesn't want to go that way, then it's gaining potential. It's like you're rolling it uphill. Okay. So yeah, on to the next question. We have 3 capacitors here, C1, C2, and C3, connected to a battery with voltage V, or EMF E right here. And we want to know, what is the charge on C2? This one is a bit tricky, so I'll give you at least 5 minutes on it. I might have spent a little bit too much time on the last one, so I apologize if you guys got bored or anything like that.
I have a question about the final, kind of just in general.
Yeah.
So since this practice exam was for the 2020 spring final, that was one that was taken online still, right?
That's right.
So will it reflect this final better than the exam 1 practice or something?
I think it's hard to say. I would say a soft yes, but they did change the course a little bit. So if you look at the actual exam, it still has lab questions on it and other things like that. So I think it's a good these questions are yes. So yeah, the questions that we're doing right now, I would say yes, are a good representation of what you will see on your exam. And as you go further back, it becomes less and less good at representing what you're likely to see. But that being said, it's still not a really good representation because they did switch from 222 to 232x. So they changed the content a little bit. And the order in which you learn stuff. So yeah, do keep that in mind.
Yeah, because the only reason I was wondering is I noticed I know the course changed too, but I noticed some of the exam 1 or 2 practices ended up being a lot easier than the actual exam 1 and 2 felt. Maybe that's just a personal thing, but
No, I think that's because they were in person and they make them a bit harder now because
Yeah.
if anyone, just to account for people who try to use their phone during the exam and stuff like that.
Yeah.
Which you should definitely not do. Please do not cheat, you guys. I saw what happened with the first exam. They gave you the honor system, and then not saying you. If you show up to SI, you probably didn't. But don't cheat, you guys. It just makes everyone's job more complicated. You guys know how to do this. Like, you put in the effort. Don't cheat yourself out of it. I do not know what happened to one of the guys. Oh no, I have no idea. I suspect it was. I suspect they don't know who it was. I suspect they were just like they heard the rumor and then they were forced you guys to take it at a certain time now. Okay, so I have 2 answers for D on this one. I'll give you some more time because I think this one, this is kind of one of the first ones that takes a bit of a significant amount of computation. But, that's a little off, Christian. Yeah, I'm not sure. It does apply here, Christian. You are allowed to do that, but you do need to be careful about how you apply it because C equals Q over V is true for each individual capacitor, but you have to combine these capacitors carefully. Yeah, so Andrew, that approach is really good. That's a very strong approach. That's how I usually solve these problems, and yeah, I think that's a good way to do it. If you like collapse the circuit down into one equivalent capacitor and then kind of break it up from there, I think that's the easiest way to do these types of problems. All right, another vote for D. I do want to say, if you guys are, when you are studying, if you guys go over the previous exams, you will find lab questions. So I know, just keep in mind, lab questions will not be on your final. So don't worry about those because they were already evil. They shouldn't have had those. And second, they get harder as you go back. That's my rule of thumb. I think like the older exams are more difficult, both because like it's further from what you guys have learned, and I think it was more of a weed out course the further back you go. This course, of course, was. I mean. I don't think this is I think it's always been a different course, but they were required to do it at the same time. Now I'm not sure. I think you can technically take the lab next semester if you wanted to. I'm not sure though. So yeah, don't like quote me on that. We can agree to disagree there, Ethan. Actually, the labs were pretty fun. I remember. Did you guys do the electron beam lab? I guess I don't know what your labs were like, if you had the lab kits or not for this class. I really like the electron beam lab. That's really cool. Like, you get to see actual electrons moving in a magnetic field. Like, that surprising behavior. It's real. It's pretty interesting to me. But yeah, I was never very good at labs, that's for sure. Freaking not great with my hands. Okay, we spent a good chunk of time on this question. Do we want to go through it? Yes, okay. Lee Soren speaks for the group. So I think all the people who did get answers answered D. So let's see if we can't confirm or deny that. So first things first is I'm going to redraw the circuit in a slightly different way, but equivalent way. So first things I want to do is fill out a battery, and then I have a capacitor here, and then a capacitor here. So I'm going to collapse those parallel capacitors down into an equivalent capacitor, and I'm going to say C2 plus C3. So it's just as they're in parallel, and capacitors combine nicely when they're in parallel. You just add them up. You got C1 here and epsilon. So now I'm gonna collapse this down into one capacitor. So this is gonna become that, and then I have this. So EMF, and then I have C equivalent. And C equivalent is going to be the following. So we got to use our capacitor combination rules. So 1 over CEQ is equal to 1 over C1 plus plus this capacitor right here. So it's 1 over C2 plus C3. So what we want to do is solve for CEQ. So we have to get a common denominator on both sides here. So what we do is multiply by C1 on both of it on the right term. We end up with the following. So C1 plus C2 plus C3 C1 times C2 plus C3. That's equal to 1 over CEQ. So now I can flip both of these fractions over. And we find CEQ is equal to C1 times C2 plus C3 divided by C1 plus C2 plus C3. Okay, cool. So we solved for CEQ, but we're not done yet, right? We're looking for the charge on C2. So we're going to look back, and we're going to use the fact that when we have two capacitors that are in parallel, like we do here, or that series, sorry, when they're in series, they're going to have the same amount of charge. So this is going back a while, but you may remember, we learned this in lecture, like the amount of charge that is on the outer plates here, the plates that are connected to the battery, is limited by the amount of charge that these have. So you can only get as much of a charge on this side as you can get on this side, on the opposite plate, I mean. So so that's fundamentally limited because this started out uncharged. So you can only get as much of that as is on the inside. So we're going to have the same amount of Q on C1 and the equivalent capacitance C2 plus C3. So what we're going to do now is figure out what Q total is on the whole circuit. So to do that, we're going to use the fact that Q total is equal to C total. And I'm going to relabel this actually as C equivalent, times the voltage. So voltage is equal to EMF, so I'm going to rewrite the voltage as E, because that's what we labeled it in our diagram. So now we have this. And now we can expand this a bit. So we have C1 times C2 plus C3. And then we're just slapping on E on the end of here. So that's equal to Q total. We're not after Q total, we're after Q2. So let's figure out what's on C1 and then work backwards from there. Okay. Well, we still have well, C is equal to Q over V, right? So we can rearrange this and we get CV is equal to Q. So if Q1 must be equal to C1 times V1. So we can figure out what the voltage drop is across C1, then we can figure out what Q1 is. We know what C1 is. So that's actually not too hard, because if we were to draw a loop around this, better way to do this is if I color it. If I were to draw a loop here and apply Kirchhoff's rules, then I'd have a voltage drop here and a voltage drop here, and that voltage drop has to be equal to this. So the voltage drop across C1, let's actually just write that down. So the total voltage drop is equal to the voltage drop across C1 plus C23, so V23. So we're looking for this, or rather, check my notes. V23, which is what we're looking for. Yeah, that's right. Minus V1 is equal to V23. So we're getting close. Like we're getting some relationships, and it feels a little off, but we're not losing hope. Okay. So here's the deal. So Q1 is going to be equal to Q total. So how do I know that? Well, we said that. Is that even right? Sorry, I need to check my notes. Yeah, that's right. Why is that right? All right, sorry. Well, it is true, and I think so. So the reason I'm confused here is because I think it should be a half. I don't know why it's not half. You should have half the charge here and half the charge here. But that is not the case. I need to think about why that is. So I'm sorry if that's confusing you guys, because it's confusing me. But anyways, we're going to keep pressing on, because this is going to get us the right answer. So yeah, knowing why that is, I'll think about it. But the deal is, that's equal to Q total. So we want to figure out V1, then V1 is equal to Q total divided by C1. And this is a number that we have. So now V2, from our equation right here, V23, is equal to Q total, which we solved for, divided by C1. So that's going to be C2 plus C3 divided by C1 plus C2 plus C3. And now we're almost there, because if we want to figure out what Q2 is, we can apply C is equal to Q over V one last time. So we have V now. We want to solve for Q, so just multiply this by, if we want Q2, we just multiply V23 by, sorry, go away. There you go. V2 is equal to V23 times C. Man, this is not going smoothly right now. So we figured out what V23 is right here, and this should be C2. And now, we're good to go. So when you plug this into your calculator, it's equal to EMF minus C2 plus C3. And when you plug that into your calculator, you get 8, which is D. So yeah, when I'm not on the spot, I will get back to you on why that Q total is equal to Q1. That's a little weird to me. But yeah, so are there any questions on that? The important part is like noting that you have equivalent charges on parallel capacitors and equivalent voltage drops across parallel ones. Yeah, sorry, that did not go smoothly. But this next one will go better. So, yeah, give me a second to think on that. But then while I'm doing that, you guys can work on this question right here. No, the charges on C2 and C3 are not equivalent, but the voltage drops across C2 and C3 are. So yeah, I might have misspoken. I think I did misspeak at many points in that explanation there. Sorry about that. These are good questions. Yeah, I'm sorry, you guys. I'm a little rusty. But anyways, this next question, we were trying to solve for E1, and it gives us a hint. So calculate E2. That hint is very useful. I do recommend you use it. So yeah, we're given the circuit. You cannot collapse this one down into equivalent capacitors or equivalent resistors. You can't do that. Oh, okay. Yeah. All right, I figured it out. So the idea is Q is not referring to the total charge on the, like, Q is really half like the charge difference, right? Because you have a plus Q on one plate and a minus Q on the other plate. So that's what's really happening. That's how we were able to say that Q total is equal to Q1. The reason we're able to do that is because Q is referring to the charge on one plate, not like the charge on both plates. I've got a drawing here that might clarify that, but yeah, that's the idea. So we're allowed to say that it is a true statement to say Q total is equal to the charge on Q1. And that's because charge on one of those plates has to be equal to the total amount of charge on capacitors 2 and 3 in the last question, because like the net charge on all of the plates that are disconnected from that have to be 0. Yeah, sorry that I dropped the ball on that. I shouldn't have forgotten that, but I did. So sorry about that. Bit of a waste of time. Is anyone stuck on this one? I think we're kind of getting into some old content. So if you need a reminder, don't be ashamed. You know, this is the time to ask. Does anyone not know where to start? All right. Well, Christian, the important thing is you remember this is about Kirchhoff's laws. All right, no problem, Caden. Thanks for coming. Yeah. So Christian, the important thing is to remember this is a Kirchhoff's laws question, which is exactly correct. So you've got two rules that about Kirchhoff's laws, and they tell you. There's two rules, and the first one you want to apply is the junction rule. So the junction rule tells you that the current in is equal to the current out. The way to use that is when you choose a loop, right? The way we do Kirchhoff's laws is we say, all right, I'm going to choose a loop, and I'm going to go through each component of my circuit. I'm going to account for the voltage drop or gain over that element. So like, if I'm doing this big loop right here, then I would like start at this plate. I'd go right here, and then I hit this junction. So I could go left or right. That's why it's a junction. And so you say the current coming into that junction there is equal to the current coming out. And so that's how we're going to solve for I2. That's what you want to do for I2. So you can use that to solve for I2. And then from there, you choose one particular loop to solve for E1. So that's how you want to do it. But remember, so the junction rule is how you solve for I2, and use the loop rule to solve for E1. So the loop rule just says I have to count. If I make a full loop, I have to have a net voltage of 0. So I say 0 is equal to E1 minus V minus 8. And the plus, you have to be careful with your signs, but like there's a plus or minus 8 here, and then a plus or minus I2 times stuff like that. Hopefully that jogs your memory a little bit. All right, so Christian got A. You guys, so I did solve explicitly for I2. So if you want to like check that intermediate step, you can with me. Yeah, so we have 15 minutes. Do you guys want me to go through this one so that we can keep the pace going, or would you rather try and solve it yourself? Yeah, that is correct. I2 is just 1 amp, and so that makes sense because so that makes sense because I3 coming in to this junction right here, it splits between going up and going to the side. So 2 are going to the side. 1 has to go up because the amount coming in is 3. So all of it has to be accounted for. Yeah, let's go through it, and then I'd like you guys to think about whether or not you want to like skip to the end to cover some optics stuff, or if you want to just stick with it. I think I didn't finish like the very last question, but there are some good optics problems that I think are worth doing. Yeah, so Christian, it's not A, unfortunately. It is the correct answer to this one is C, or sorry, not C, E. Well, let's talk about it. First things first, just what I was saying last time. Like if I have 2 capacitors that are in series like this, then the amount of charge is on one plate. That's what Q is referring to. So like this is exactly the same situation as we had up top here with the blue line. right? We said C1 is equal to Q total. Well, Q total is, the maximum amount of charge you're ever going to have is Q. And that's the idea here. So hopefully this drawing makes a bit more sense on why we're allowed to say Q1 is equal to Q total. This step right here is what messed with me, which is why I kind of dropped the ball. But anyways, we're not doing that question. We're doing the other one. So number 7. I'm going to draw the circuit, try and do it kind of quickly because we're running out of time here. Got some resistors like that. Okay, so we're looking for E1. We know E2, and we know E3, and we have R1, R2, and R3. I3, I2, I1. Okay, so I'm going to use the junction rule first to solve for I2. So if I take this I3, it's still going to be going this way, and then it hits this junction right here, and it's got this is I1 moving that way, then we have I2 moving up, and then I3 coming in. So if I were to put that in the equation, the junction rule tells us I3 is equal to I1 plus I2, right? So current coming in is equal to current coming out. That's all it's saying. So we want to solve for I2, so we say I3 is equal to or I3 minus I1 is equal to I2. Oh God, that's really weird. Okay, never mind. That's weird. Is it gonna erase? Just won't let me erase that. Okay, so we got that. When you plug that in, it's 1 amp, right? Because it's 3 minus 2. So we've got that neat. Now we want to solve for E1. So what I'm going to do is I'm going to take the following loop. So I'm going to go start at this plate of E1, then I'm going to go up and around, and then I'm going to come down, and then I'm going to go like this, and complete that. So this is my loop. It's the leftmost loop. And to really complete it, what we're going to do is we're going to start with 0. We're going to say 0 is equal to, well, what's my starting voltage? It's E1. I'm starting at the positive plate of this battery, E1. So I'm going to have a voltage of E1 if I took my voltmeter and dragged it along. Okay, then I'm going to hit E2 right here. And so E2, I'm going to have a voltage drop because I'm going from a positive to a minus. So that's a voltage drop right here. Yep. And then I'm going to have a voltage gain because I'm going against the current across a resistor. So it's I2 minus R2. And then I go, and the only other place I have is R1 and I1, and I have a voltage drop right there. So it's I1, R1. So we have this, and we're trying to solve for E1. So we're going to do a bit of algebra. We're going to find out E1 is equal to E2 minus I2 R2 plus I1 R1. Yeah, so it can be very difficult to like choose which loop. It takes a bit of experience and practice, but yeah, you don't actually need R3 for this one, unless you're doing another version, in which case you do. Yeah, so now we know everything on this side. We can plug these into our calculator. So it's going to be 8 minus 3 plus 4 when you plug that in, because it's going to be 2 times 2, I1, which is equal to 9 volts, which is E. So E is the correct answer here. And we've got 10 minutes left. So, this is, yeah, like I think it's a good idea to practice this magnetic field stuff, and the optics stuff is fresh in our brain, but at this point, if you guys have questions on anything specific, want to cover a certain topic, now's the time to ask, because we're kind of running out of. Yes, the loop can go any direction you want. It can go counterclockwise. You just have to account for the minus sign. So if you go counterclockwise, then it's the same thing as multiplying the equation I wrote down as by minus 1, because instead of voltage drops, you'd have voltage gains and vice versa. That's an excellent question, though. Yeah, so yeah, if no one has any preference, then we'll just keep going. But I am perfectly happy to jump around this test if you guys want to cover a certain topic, because like this is my last chance to help you. There is not a complex impedance question on this exam, which is why I kind of skipped over that on the equation sheet. I don't think there'll be much on your exam either. I can't say it won't be on there because it's possible, but yeah, there was not a question that required you to do anything with complex numbers.
On the question we just did, in like the loop one equation where it's 0 equals the E1 minus E2 plus I2 R2 minus I1 R1, why is it like plus I2 R2 when that's where it's going against the current?
Because usually resistors are voltage drops, right? So if we agree with the current and that's going with the resistor, then it's a voltage drop, because resistors resist current. That's a voltage drop. So if you're going the opposite direction, it's a voltage gain. That's how I think about it.
Okay, thank you.
Yeah, it's a good question. All right, so no one has any. It doesn't seem like anyone has any particular topics they want to discuss. So if that's the case, we're just going to keep going, which is fine. Yeah, okay. So we've got number 8 here. Ignore this line. That's not part of the question. That's from me snipping it. We've got a capacitor connected to a battery. It's fully charged and then hooked up to a resistor and allowed to discharge. So we want to know, what is the energy in the capacitor at a certain time after it's first connected to the resistor? So there's kind of a lot happening here, but you guys definitely can do this, I promise. All right, so is anyone completely stuck on this one? Doesn't know where to start? All right. That's good. I mean, knowing where to start is like, it can sometimes be more than half the battle for these physics problems. I know in my thermal physics class, yeah, knowing where to start is the hardest part, especially with thermal, because like you can't draw a picture. It's all about statistical mechanics, so it's too much to draw. Okay, we spent a decent amount chunk of time on this one. Well, actually, I'm just getting antsy because. All right. One vote for A. Does anyone have anything to do at like 4? Or can I let the session run a little bit longer? Because I'd like to get through a few more questions. 1 or 2 maybe. That is a long time to be hearing my voice, though. I understand if you don't want to. Well, I've got something at 5, so I can't stay for super long. But yeah, I'll make this one a bit longer. Let's go through this just for the sake of time. I'd like to go through it. The way we solve this one is really just by applying equations. Just as like, just to remind you, like what's happening here is we charged the capacitor and now we're hooking up to resistor and allowing it to discharge. So the equation we're gonna use is the following one. So this is Q at 0. So this is the equation we want to use. So we know tau is equal to RC. That's on our equation sheet. So we know it's RC and not like LC or anything like that because we don't have an inductor. And we're told it's a DC circuit, so we don't have to worry about omega. So figuring out what Q naught is pretty easy because when you do that, it's just C times V. Like that's true because we were told that it charges completely. It's to its full charge, so Q naught is equal to C times V. That's how we figure that out. Okay, so the only thing left to do now is plug this into our equation that describes the energy stored on a capacitor. So that's equal to Q squared divided by 2C. So the reason I know to use this equation is because I know what Q is and I know what C is, and the other ones I don't. There's one unknown I'd have to solve for. So this is the best version of this equation to use. So we're just going to plug in our modified version of this up here. So I'm going to do that on another line. I'm going to say it's equal to, it's equal to C times V times E to the minus T over tau squared divided by 2 times C. All right, so now we can just, that should be an E. So now we can just distribute the square and cancel out one of the C's. We get 1/2 CV squared E to the minus T over tau T's 2T. Okay, so we've got that, and when you plug it into your calculator, you get a value of 0.1487, which is about 0.15. The answer is C. So it's an answer. It's in units of joules. So yeah, that's how you do it. It's just a matter of doing a bit of algebra and the plugging in. So the plugging in is a bit tedious to do on your calculator, but you can do it. I'm sure. Yeah, Ethan, it's okay to mess up scientific notation. I'm 3 years into a physics degree and I keep forgetting which way to move the decimal point. With like the minus and the plus, I always get confused on that. So yeah, happens more than I want to as well. So it is 4:01. If you guys have to go, first of all, thanks for coming. And it's been a good semester. I appreciate everyone who showed up to any SI sessions. Do appreciate that a lot. And hopefully I see you around. I hope you have a great summer and good luck on your finals. But if you can't stick around, I'll probably keep this going a few minutes later. I can't, like I said, I do have something going on at 5, so I'll probably go until like 4:15 or 4:30, somewhere in there. Don't tell SI I did that. I'm doing this. Yeah, so number 9. Yeah, thanks for coming, Kaya. Yeah, I really appreciate you showing up. Yeah, thanks, you guys. Those of you who are sticking around, yeah, we're gonna work on this question, number 9. We got an electron moving with speed of 4 times 10 to the 5th meters per second, moving in a uniform magnetic field of 12 teslas, and the velocity is at an angle of 30 degrees. So this is our diagram right here. And we want to know magnetic force. That's a good question, Ethan. I don't actually know. I'll check. It's been a long time since I made this playlist. Yeah, it is a remix. This is the Stephen Walking remix. All right, is anyone stuck on this one? Doesn't know where to start? All right. Yeah, we'll probably, okay. Well, you shouldn't need the charge of a proton is actually the positive charge of an electron. Oh, it's 1.6 times 10 to the minus 19. Yeah. I think that is on your equation sheet. It's on the first page. Yeah, and there's actually a mistake on the answer key for this exam that we're going over. Number 11, which we're almost to. They forgot to multiply by 2. You're right, Christian. It is B. And I'm not just saying that. It is actually B. Let's go through it just so that we can keep the pace up. It's just the three of you guys now. So you got personal access to the SI here now. But here's how we solve this one. So we're going to use the following formula. So this is on your equation sheet. You don't have to have this memorized, but all I'm doing is leaving off the E field here. Because, yeah, so the E field is gone because, yeah, it's an excellent observation, Ethan, but it's 0, so we don't have to write it. Yeah, I can see. Yeah, you don't have to worry too much about that. So what we're going to do is take the magnitude of this expression because we can use the right-hand rule to tell us the direction, and we don't have to worry about the vectorness of it. So I'm going to rewrite this as just the magnitude of FB is equal to Q times V times B times the sine of the angle between B and B. So that's a vector identity. So whenever you're doing the cross product, the magnitude of the cross product is equal to the magnitude of two vectors times the sine of the angle between them. Now, it's just a matter of plugging in numbers. When you do, you get a number of negative 3.8 times 10 to the minus 13 newtons. So once you have that number, you can actually just pick it. So there's no other number with this magnitude. So you could just pick it, but the directionality we can think about. So our diagram looks something like this. So B is pointing in this direction and V is pointing in this direction. So if we do the right-hand rule, that's going to tell us that the resulting vector F is pointing, is not equal to, it is proportional to a vector that is pointing into the page. So it would look like that. That's not a vector. So that's the direction F is pointing. But remember, we got this minus sign right here. So that's why in the listed answer, it says it's coming out of the page. So B is the correct answer here. I have time for about one more question. Let me see if there's a particular one that I want to do. Yeah, I don't think so. We'll just do the next one. Yeah, because I can almost guarantee there'll be a problem similar to this on your exam. There's a problem like this on my E&M final, or not E&M final, but my E&M test most recent one. So these loops and wires don't go away. Yeah, so the reason why the direction was into the page is because if we take our 4 fingers and point them in the direction of V, and then curl them towards B, then our thumb is pointing towards into the page. So we use the right-hand rule, we get that. And then the minus sign tells us it's really the opposite direction. So the correct answer is B here, out of the page. And so the reason it's out of the page is because it's the opposite of into the page. So the right-hand rule, take fingers, point them towards V, and then curl towards B. Remember, we have our palm facing in the direction of B. If we were to reverse that, like take B and flip it to the other side, then we'd have the opposite thing. So if B was sitting like this with respect to these 4 fingers, then I would have to flip my palm in order to turn my fingers towards them. And then now the direction would be pointing out towards me. Yeah, no problem. Yeah, I think I'm actually fading here. My voice hurts a lot. So I think this will be the last question I do, but I'll stick around in case you guys have questions for me. Hopefully this is helpful. I don't know. Maybe this is just 15 minutes of fluff, but yeah. I would be happy to. I mean, I'm surprised you guys, this is the song that you guys really enjoy. Yeah, I'll link it to you. Yeah, follow me on SoundCloud. You'll find out my tastes are very different than what are in this playlist. Well, my dream job, if it wasn't being a physicist, it would be being a DJ. And that's true. I would love to be a DJ. Never actually like looked into doing it though. I have a free DJ software downloaded on this laptop. I've used it like a few times and that's it. Maybe that's what I'll do with my summer. Last summer I learned how to throw boomerangs. Maybe this summer I'll learn how to DJ. Do you have to go, you? All right. Yeah, I am. Thanks for showing up, you. It's been a pleasure having you. I wish you the best of luck on your finals, and I hope you have a great summer. Yeah, thanks for coming, man. Thank you. Ooh, I don't know, man. I see. I played chess back in like elementary school. Chess is hard. It's really hard. Like. Yeah, it's not a bad game. I tried to get back into chess in high school, but I couldn't do it. Ouch. Yeah, I'm pretty bad as well. Yeah, you know, it's probably a good. Let's go now. I don't know. During finals week, I would. It's a bad idea for me to do that because I know I would just end up. I know I will lose. Yeah, I can't try and get into chess now because I will instead of study. All right. Let's. Can I go through this one? Okay. So yes, that is one of the equations you're going to need to use, and you're also going to need to use the force on the wire equation. Yeah, let's go through this. This will be the last one, you guys. I've got to go. Thanks for sticking around. I do appreciate it. But yeah. So here's how you do it, Ethan. So this is a square, just trust me on that. So first things first is we're going to label our diagram with some letters. So this is our distance D, and I'm going to call this distance L. So it's square, so it's all the same thing. So first things first, we're going to call this I1 and I2. I said first things first. This is like the third thing I've done. Oh my gosh, Ethan, that's awesome. I am very impressed. Thank you. You should don't let me take credit for your accomplishments though. That's great. So yeah. So what we want to do is B is equal to mu naught I1. So what we're going to do is describe the B field due to the this wire right here. And then we're gonna each electron in this wire here is going to experience a force, and so that's going to cause a force in the entire wire. So and then we're going to break this square up into four chunks. It's equal to 2 pi. That is a terrible pi. Hold on. 2 pi times x, where x is the distance from the wire. So that's the B field that we have, and so we're going to use the fact that a little bit of force is equal to I times dl cross B. So if we integrate both sides, right? Because every time we have constant direction for L. So L and B is going to be pointing into the page. So it's actually going like this for us. So B is going to be pointing into the page at every point along this wire. So F is going to be equal to IL times B. Yeah, so we've got that, and now we can apply that for each one. So let's think about the direction of the force. So B is pointing into the page at every point. Why do I keep doing that? That's really weird. So B is pointing into the page at every point to the right of our wire. So that means that we have I cross B. So our thumb is pointing to the right for this one. That's the left, not the right. So I call that F1. Then we do the same thing. We have F2 pointing this way, F3 pointing this way, and F4 pointing this way. So we've got that. And now, so immediately we can see F2 and F4 are going to cancel out. So we can safely ignore those. Because every point that I pick right here is going to have an equal point right here that has a force pointing in the opposite direction. So that those forces are going to cancel out. So really all we have to do is figure out what F1 is and F3 is, and then add those two forces together. So F1 is equal to, so this should be I2. Let's be careful about that, right? Because the current is what's feeling the electric fields. We have to label our currents in order to really avoid confusion here. So F1 is going to be I2 times L, and then B is going to be equal to mu naught I1 times divided by 2 pi times D, right? Because that's the distance to the wire. So it's going to be mu naught I1 divided by 2 pi D, and then F3 is the same thing, but now instead of D, it's going to be D plus L because we're further away. So there is a net force. You know, your initial intuition might tell you, well, there's no net force because it's nice and symmetric, but it's not quite as simple as that because the B field falls off like 1 over R. So it's going to be, you have a weaker B field, so a weaker magnetic force when you're further away from the loop. We have that. Now we add these together. So they're pointing in opposite directions. We'll say F3 is in the positive direction. So F net is equal to negative, I'm going to pull out all the common factors, I1, I2, L, divided by 2 pi. And then we multiply this by 1 over D minus 1 over D plus 1 over D plus L. So when you plug those numbers into your calculator, you get 1.34 times 10 to the minus 6th newtons, which is Yeah, so there's like a lot of moving parts here, but once you break up the diagram, it's not too bad. All you have to do is really recognize that. All right, so do you guys have any questions before I wrap it up? I will stop recording.